Welcome to session 19 in our series on electricity and magnetism. In the last several sessions, we found that alternating current has some distinct advantages over direct current when we're trying to move electricity long distances. Alternating current allows us to use the transformer, which can raise the voltage, lower the amperage, and send the electricity long distance over reasonable sized conductors to another transformer, and where we lower the voltage, raise the amperage, and it's a voltage that's safe for us to be near. Now it turns out that alternating current is actually easier to produce than direct current. Let's take a look at a little device that you've seen before. So all we need to do to produce electricity is have relative motion between a magnetic field and a conductor. And to make that worthwhile, we need to have a strong magnetic field and some kind of, multiple turns typically of the conductor. So what I'm going to do is I'm going to move this magnet, and I want you to watch the little motor, a little paddle on the motor. So here is plus, minus, plus, minus, plus, minus. And that's all there is to alternating current. We now have alternating current. And we didn't have to use a commutator and brushes, which are a maintenance problem for something that's running all the time. And we didn't have to use diodes. And like I said before, we can raise and lower the voltage using a transformer when we're working with alternating current. Now, almost 90% of the households in the United States have an alternator, a generator that produces alternating current. And it just happens to be under the hood of the car. All internal combustion engine vehicles have an alternator. And that alternator produces alternating current internally. And then that's converted to direct current because it has to work with the battery, which is a direct current device, and all the accessories that work with direct current because they must work with the battery. So let's take a look at what's inside. Now, the alternator we used for our experiments before, where we were transmitting electricity using the transformer, is also an alternator out of an automobile. Let's take a look at what's inside. So this part is stationary, and it's got windings embedded in a slotted core of steel. It's laminated. Remember, whenever we have changing magnetic fields, we want rapidly changing magnetic fields, we want the core to be laminated so it doesn't waste a lot of energy creating electrical currents in the core. That's all useless energy. The magnetic field that cuts through these coils is generated by this rotor. Now just ignore these little green wires that I have soldered on here. This is for something I'm going to show you a little later. They did not come with the rotor. So this part here produces a magnetic field that cuts through the stationary part. It could be a permanent magnet, but the problem with making using a permanent magnet for the rotor of this alternator is that we need to regulate the voltage. The voltage, say, of an automobile alternator has to stay within, let's say, 13 and 15 volts, preferably 13.5 and 14.5, a very narrow range. And yet the speed of the alternator range can be vast, from when the engine is idling in a driveway to where it's going down the highway and suddenly you go into passing gear. So we can't change the number of turns. It's fixed once it's manufactured. The speed varies. The only thing we can vary is the strength of the magnetic field. So let's take a closer look at that device. Here's the stator and the rotor, and inside here are windings, round and around and around. They get their power through these two slip rings right here. This is a bearing, but these two are slip rings, and there's carbon brushes that rub up against that, providing a plus and a minus direct current, and then that magnetizes one end, and I've picked this as the North Pole, and the bottom is the South Pole, and these little fingers that emanate from that side are going to be North Poles, and then these little fingers from the South Pole are going to be South Poles. So we have a magnetic field going from north to south, north to south. Now let's take a look at what that field ought to look like. Here is, this is what you ought to be looking for. Let me zoom in on that a little bit so it's a little clearer. Okay. So you can see, here's the North Pole in red, and the field comes out this way. We've talked about, we define the direction of the magnetic field from the North Pole to the South Pole, from the North Pole to the South Pole. So this field is cutting through, all these fields are cutting through these windings, because the steel core is sitting very close to this. It's reaching across, going through the outer core and back. Now I'm going to create a magnetic field, an actual one for you, using little particles of steel, little filings. So if you will just bear with me, this will just take a couple of moments here. Let's put this device on here, and I'm going to hook up a 1.5 volt battery. Can't make it too strong. The little particles will just kind of clump and get drawn to the powerful magnet. So we're going to do it with a weak magnetic field. We're almost there. A little bit more. I think this is coming out good. Okay, now I'm going to tilt this, and hopefully it won't slide. Magnetic field is very weak, and I have to be careful as I tilt it. And I think you can see, if you're careful, you can see the pattern there. Let me find, I think we're better off there. Let's add a little bit more to that. I'm going to tap it. Should have tapped it earlier. There we go. Ah, it slid. Well, you saw a little bit of it. Disconnect that, and So this was the pattern we were looking for that was cutting through those coils. Now, if we take that alternator, put it on its end, and then we make it a lot bigger, we pretty much end up with one of those. That's a generator room at the Grand Coulee Dam powerhouse, and you can tell how big they are from the size of the ladder there. That gives you the human scale. And inside is a rotor that has some resemblance to what I showed you. These are a bunch of north and south electromagnetic poles. Yeah, we use electromagnets in these big ones, and because they require the control of the voltage as well. The speed is fixed very precisely in order to get 60 cycles AC per minute, per second. And so that can't change. And of course, these are spinning inside of a stator whose windings are fixed. So the only thing we can vary in order to keep the voltage at the right level, depending on how much power is being used and voltage drop there is in the transmission lines, is to vary the magnetic field a little up or a little bit down to kind of feather in the right voltage at the end of the line. Now, I'd like to finish up by kind of going back to the automobile alternator, and this stator has 3 windings actually. It's a 3-phase alternator. The commercial ones, the big ones I showed you, are also 3-phase. All of the power plants use 3-phase alternators. Let me give you a close-up of that winding. It's a little easier to see right here. If you look, you will see 3 overlapping windings. There's 1, there's 2, there's 3. There's 1, there's 2, there's 3. That happens all the way around. And so all of the ones that I called 1s are connected to one circuit. All of the 2s are connected. All of the 3s are connected. Each one of those, all the 1s produce a sine wave, all the 2s produce a sine wave, all the 3s produce a sine wave, and they're out of phase with each other, kind of equally spaced. The reason we use 3-phase power is because we can produce a more compact alternator, and also we can transmit more electricity over the same amount of conductor, whether it's aluminum or copper. We can send more electricity over the same amount of metal as efficiently. So, and also at the other end, large commercial motors in our factories and buildings operate more efficiently, they're more rugged, and again, they're more compact. So 3-phase has a lot of advantages. But that's what we produce in our automobile alternators. Let's take a look at what that phasing looks like. Let's start up our alternator. So we're using that alternator, and what you're looking at is single-phase power, one of the 3 phases. Now, I can't show you all 3 because this oscilloscope only has 2 inputs. It only handles 2 channels. I'm going to add a second phase, and you'll see the second phase is in yellow. If I could do 3, it would end up right here in this gap. And so you'd have 3 very evenly spaced alternating current sine waves. Now those are fed through diodes, which convert alternating current into direct current. And I'm going to flip the switch here, and we will compare a single phase with the direct current. So here's our single alternating current sine wave, and there's the direct current voltage that's being provided. And you recall in one of the earlier phases I said when we rate alternating current, we don't base the voltage on the peak. We base it on a special average. It's about 70% of the zero to peak voltage. The reason the direct current is sitting up there as an average is because we have 3 phases feeding into it. So it's filling in the gaps that a single phase voltage would have. Well, I hope you've enjoyed this session, and thank you for coming, and hope to see you next time. You take care.